Hi, this is Jian Weng, a fourth-year PhD candidate from UCLA. In this talk, we are going to claim that generality is the key dimension to accelerator design. Based on this insight, we present an automated flow for accelerator generation. Therefore, by the end of the day, we will have a framework that automatically generates a specialized accelerator for a given set of applications. Towards this, our very first question to answer is what is the scope of our design space? To start with, we should look at some prior domain-specific accelerators. However, they look so different from each other because they are specialized for different domains. But still, we believe there's a deeper way to look at the differences. It's not about the domain, it's all about the specialized idioms. What aspects are general, and how are these aspects formed into specialized idioms? Let me give you a few examples. Let's first talk about 电脑, a DNN accelerator. Its main idiom is a reduction tree followed by activation function. Memory structures are highly specialized with dedicated memory buffers for input, output, and weight tensors. To encode the memory access pattern, the idiom is just general enough for rectangular memory access. Next is Q100, an accelerator specialized for database query, which makes different trade-offs. It has very efficient support for more general data-dependent control flow, like join, sort, and data partitioning, but has no support for general memory access. Only continuous sequential memory access are supported. Last but not the least, Grafting is a graph processing accelerator. It has general support for indirect memory, remote atomics, and flexible load balancing, but it can only support synchronous parallelism, and the programmer should control the data reuse on the scratch pad. After looking at all these accelerators, we find that accelerators are different essentially because they make different idiom choices on which aspects should be general. This is achieved by selecting and composing a set of appropriate idioms. Here we show 5 such dimensions with different idiom choices. These design decisions must be made carefully because each generality is expensive in terms of area and power. Therefore, a universal accelerator is probably not a good solution, but a comprehensive set of idioms can form a universal design space. Then our main idea becomes that we can express each design point by composing a set of simple hardware components like processing elements, switches, and so on, where each such component can optionally choose some different idioms. We call this representation an architecture description graph. To demonstrate the capability of expressiveness, here we depict the two very different accelerators under this representation. 电脑 is a domain-specific accelerator as it has no flexibility in computation and data path idioms. On the other hand, plasticine is a domain-agnostic accelerator as its topology, routing, and access pattern have more general idioms. So here we come to our proposed framework. Our proposed framework DSHN uses the architecture description graph for accelerator design generation. More specifically, it uses a CLLVM compiler to iteratively search for a optimized ADG for a set of input applications. The candidate hardware evolution is guided by hardware-software affinity evaluated by analytic models. We evaluate our framework on a few different workload sets, starting with a same and general accelerator. Where there are still many optimizations not implemented yet, the framework can already save significant amount of area. More importantly, the trade-offs depends on the target workloads are exploited successfully. For example, sparse CNN needs a much more general network, while mesh-to-it needs a more general set of computational units. All these trade-offs are derived automatically in the exploration. So much for the evaluation, and let's move on. One looming challenge is the uncertainty. In other words, how much extra cost we are willing to pay to over-engineer the accelerator so that it can effectively handle the future potential applications. To achieve this, we should expose interfaces as a knob to the uncertainty in order to convey the broad facts that how programmers know about the future applications. We think these are interesting open questions for our future research. To conclude our talk, generality is the first-order consideration for accelerator design. Generality needs to be reasoned about during accelerator generation. And also, we should take the uncertainty introduced by potential future programs into account. Thank you for listening. I'm looking forward to seeing you on April 15 at Plus LATTE workshop.